I'm going to now briefly summarize some of the ideas in the paper Combinatorial Decision Dags, a natural computational model for general intelligence. And these ideas really have multiple roots. I mean, on the more philosophical and conceptual side, they're rooted in the ideas of Spencer Brown from his books Laws of Form, which gives this sort of formal logic of paradox and contradictions and imaginary truth values rooted in a concept of paradox as related to time and experience. And then the work of Lou Kaufman, who was built on laws of form in very complex and subtle mathematical ways. I encourage everyone to look at his website. But in addition to being inspired by these philosophical and mathematical explorations, which are founded on a very simple idea that drawing a distinction between two things that are different is the most basic thing you do in the basic operation of the mind, and you want to build up everything in the mind and world from just distinctions of distinctions of distinctions. So as well as being inspired by the idea, hey, why can't we come up with a universal computational model that as much as possible is based on distinctions of distinctions of distinctions, I'm also motivated here somewhat by practical considerations, in looking at something I talked about in another talk here at the AGI conference, how to design a better programming language framework for integrative multi-paradigm AGI systems such as OpenCog. So what we're calling designing an Atomies 2.0 programming language for a new version of the OpenCog atom space. A programming language like this, needs to have some quite subtle and complex representations under the hood in its guts. And part of my thinking here was, when you sift through all the syntactic sugar of a Atomies 2.0 AGI programming language, maybe you want to get to a sort of computational representation which is particularly suited for cognitive processing and AGI. So I'm trying to get at what is that computational representation here. One of the ideas I'm going to look at here is logical entropy. And logical entropy is a different way of measuring uncertainty than Shannon entropy. So basically, the logical entropy of a partition is the percentage of all pairs of elements that are put into different partition cells within that partition. I've generalized that in the paper you can find on arXiv called graphtropy to go beyond partitions. So if you look at what's called a distinction graph, a graph where the nodes are observations and there's a link between two nodes if those observations are indistinguishable to a given observer, then the graphtropy, which is a generalization of logical entropy, is just basically the number of links in the graph divided by the square of the number of nodes in the graph. And I think both logical entropy and graphtropy are important concepts. One of the things I was looking for in a sort of cognitively suitable program representation is that when you make a program bigger, the logical entropy increases. And the relation between logical entropy and Shannon entropy in a program representation context is something I'll get to in a couple moments. So one of the core ideas here, getting back to the philosophical roots, is I want to characterize a computable function, a program that takes inputs and gives outputs. I want to characterize it as the set of distinctions it makes between its inputs. And this is not really such a radical idea, but you can see in this way a program is a partition, right? Because if two inputs go into the same output, we can rate them as the same. They're in the same partition cell. If two inputs go into different outputs, then they're going to different partition cells. And then if you're given a distribution over possible inputs, you can calculate the logical entropy of the program as a partition, as a maker of distinctions. Now, interestingly, if you make a sort of optimal, like a minimally sized binary decision tree representing what that program does, how it maps inputs into outputs, the average depth of this optimal binary decision tree, the average length from the root to the leaves, is the Shannon entropy. So in a way, Shannon entropy is like runtime complexity, and logical entropy is like algorithmic information in a way, very, very, very vaguely speaking. Now, the next notion I want to introduce is the concept of pattern. And if you look in the works of Spencer, Brown, and Kaufman, the notion of pattern is all over the place. In some of my earlier work, in my attempt to come up with a mathematical foundation for cognition, I tried to view the mind in general as a system for recognizing patterns in itself and its environment, and in particular, for example, in recognizing patterns in which of its actions tend to lead to which results, in which environments and contexts. The concept of pattern, as I defined it underlying this cognitive theory, was a pattern is a representation as something simpler. And in algorithmic information theory context, basically that means if you have a bit string, a pattern in that bit string is any program shorter than that bit string that produces that bit string. But the notion of pattern is a little more general than that notion of algorithmic information. We can formalize pattern in terms of distinction if we have, say, a function rho, a relevance or invariance function. Rho tells you which distinctions you care about and which ones you don't care about, which are relevant and which aren't. So if you then have a program F that makes certain distinctions between inputs and by giving different outputs for them, you could say P is a pattern in F if it makes all the same relevant distinctions as F does, but fewer distinctions overall. And that, under the right assumptions, boils down to being the same as the algorithmic information theory characterization of pattern. You can extend this in various ways. You can extend it to what does it mean for one program to be an approximate pattern in another, and you can also extend this into a quantum pattern or a quattern, which I go over in the paper, but I'm not gonna talk about here. I mean, to look at quantum patterns, you look at a distinction as not being either or probabilistic, but you look at a distinction as being weighted by an amplitude, a complex number, and then you can come up with a generalization of this notion. And as I said, that if you want to take into account something like runtime complexity, you could say, well, we need the optimal binary decision tree for the pattern P has to have lower average root to length than the optimal binary decision tree for F that it's a pattern in, and that means sort of the Shannon entropy of that partition of the pattern is appropriately related to the Shannon entropy for the function, the program that it's a pattern in. So you can do a lot of other things to quantify patterns, but what I'm more interested in here is using the notion of pattern to extend the representation of programs as decision trees into something that's more AGI-ish and more robustly general purpose. So going from a decision tree to a decision DAG is nothing new. Basically, if you have a binary decision tree which has repeated subtrees, you can just leave only one copy, and anything that pointed to the other copies points to that one copy, and that goes from a decision tree to a decision DAG. But what I want to do here is something a little more general. If you have two decision trees that are not copies of each other, but decision tree X could be produced from decision tree Y by some other program that's smaller than decision tree X, right? So then in that case, you could get rid of decision tree X and replace it with the program for computing it from Y and a pointer to Y. So this is, you can think of as pattern-based memoization inside a decision tree. So if you do that, and if you allow decision trees to take encoded versions of other decision trees as inputs, so let a decision tree act on the whole structure of a decision tree, then by putting recursive application of decision trees to decision trees together with pattern-based memoization, then you get something quite general. And I show in the paper that this is basically just a different way of looking at SK combinatorial logic, which has universal computation power. So the conclusion you come to is basically you have decision trees, which are single feature queries and conditionals. You have recursion, basically being able to encode a decision tree to feed into another decision tree. You have basic pattern recognition, pattern-based memoization, static pattern recognition, and then, ta-da, right? Then you have universal computing, and you have also a neat relation with logical entropy. So if you're using a combinatorial decision DAG of this nature to represent programs, then you find that adding on to a program, so adding an extra distinction to a program, can never decrease its logical entropy. And on average, bigger programs, this representation of higher logical entropy, which is a very elegant relationship between programs in this representation and logical entropy. I mean, there are representations between algorithmic information and Shannon entropy that are well known, but they're much uglier and messier than this. What I show here is if you assume a nice representation for programs, you can get a much crisper and simpler representation between program size and entropy, but you have to shift from Shannon to logic entropy. And if instead of a program in itself, you're looking at a program as observed by a particular observer who may have inaccurate vision, then you have graftropy instead of logical entropy, and you have similar results. This also holds with quantum logical entropy if you're building programs with quantum patterns rather than classical patterns. So, this is cool philosophy and it's cool math, although I haven't had time to write out all the proofs as I'd like to. But it may also actually be relevant to building AGI systems. And I'm not sure, this is research I'm in the middle of, but if you're trying to build like an Patternbased 2.0 interpreter, so a system that implements the programming language logic optimal for an integrative AGI system, like an OpenCog system, to be fast and effective and easy to use, what's deep in the guts of that Patternbased 2.0 interpreter? Well, maybe what's deep in the guts of that Patternbased 2.0 interpreter is a combinatorial decision DAG pattern-based representation. I mean, it's not that edgy. Like decision DAGs are well known in computational complexity theory. Combinatorial logic with not just S and K, but more combinators. I mean, that's inside all sorts of functional programming interpreters. But by putting the decision DAGs and patterns together, you get a different way of getting at combinatorial logic, and something that connects with logical entropy and graftropy, which are very close to the information theoretics of learning theory, probabilistic logic, and so forth. So I think there's something here that can make this representation valuable in the guts of an Patternbased interpreter. So this may actually be relevant. So not at the layer of AI algorithms or even AI languages, but at the layer of how to efficiently represent knowledge inside the guts of the AGI language in which the algorithms are programmed. But we'll see if that cashes out. If not, at least it's some cool ideas. Thanks. And of course, if we want to implement AGI systems on quantum computers, and we don't have the hardware for that yet, then the quantum version of these combinatorial decision DAGs may also be quite interesting and may tell you what your quantum AGI Patternbased, your Patternbased 3.0 should compile into in the guts of your whizzy new quantum computer. So the math can have a quite lasting value to help with implementation across multiple stages of practical system design. At least that's the hope.